Welcome all. Thank you for tuning into my channel. So if you are new to this channel, please don't forget to subscribe. So today I'll show you how to calculate the CDP properties, concrete damage plasticity properties required to enter in ABAQUS. So first we need to calculate the strain, that is epsilon c in h equal to epsilon c minus sigma c upon e naught. This is equation number 14. Once we get the strain, so these strains are called the inelastic strain that you found in concrete compressive behavior. By entering in ABAQUS, you enter the values like yield stress, inelastic strain. So that value, if I want to show you, I have some values. So this is the inelastic strain. So this inelastic strain we calculate from using this formula, equation number 14, epsilon c raised to the power in comma h equal to epsilon c minus sigma c upon e naught. And once it is done, uh, then here the strains are calculated for corresponding stress. So what happens, we assume this stress, these stresses are assumed by us. We assume these stresses, and for these stresses the corresponding strain is evaluated. And next, for damage parameter, we use the inelastic strain will be same, and these damage parameters will be calculated using DC, this formula, that is 1 minus sigma c upon sigma c u. Now this formula is used to estimate the DC. And next we have to estimate yield stress. Just avoid this. So next we have to estimate the cracking strain for tensile behavior. So in tensile behavior we called as cracking strain, and in compressive behavior you called as inelastic strain. So if you check here, the yield stress also assumed, yield stress are again assumed, and corresponding cracking strains is estimated. And uh, this is estimated using this formula here, epsilon t ck h epsilon t minus sigma t upon e naught, which is 20, equation 20. Next we need to estimate the damage T, that is tensile damage, which we are getting here. So this will indicate the damage value 1 minus sigma T upon sigma T naught. Now as we do not have the experimental data, so if you have experimental data then you can proceed, else this is the paper I am referring. So here, over here they have mentioned, they have used Kent and Park model. So we'll be also using the Kent and Park model. This model will be used to estimate the stress strain behavior. We'll be calculating the stress corresponding to, sorry, we'll be calculating strain corresponding to stress using that model. So this is the formula that we'll be using. So that formula I have copied here. This is the formula we'll be using. And here epsilon c dash, which is at the bottom, you see this one epsilon c dash will assume at 0.002, which is given in this paper. See here, this 0.002. So we need this strain. We have to use some model, because until unless you have some experimental data, if you are going through experiment, you'll have this stress strain behavior, so you can get it. And we do not have this stress strain behavior, so we can get the data using this. So the model says that up to 0.002 it will be this, and after that it will behave like that. So here epsilon cu is the ultimate point, I would say, and c naught is uh, yield stress. So we c naught we are considering as 0.5 cu. And here for tensile behavior, this graph is this graph is for tensile behavior, and this is for compressive. For tensile behavior we take ultimate tensile strength, sigma t naught. So using all this formula, we'll proceed to calculate. So this is my Excel file I'm going to prepare. So here first we'll calculate for M30 grade. So for that I have entered these names. I want to calculate for M30 grade first, just to verify whether my calculations are correct or not. So if I made a mistake, it will show me. So this is the equation we'll be using for estimating the stresses and the strains. So that equation is simplified. This equation is simplified and in a way to get a quadratic equation, and that strain corresponding to 0.002 up to 0.002 will have a different stress behavior, and after 0.002 will have different stress behavior. The graph itself shows this is the Kent and Park model. Also, when we don't have experimental data, we need to use this type of model to get the stress strain behavior of concrete for concrete damage plasticity. And the yield stress will be taking as 0.5 times the ultimate stress. So this is the quadratic equation that I have simplified. So this sigma c equal to sigma cu. So these complete equation have been simplified, and they will be taking M30 grade concrete here. So the ultimate strength of the concrete will be 30 Newton per mm square. So that 0.5 times cu. So here this is the quadratic equation. That equation have been simplified in a way to get the quadratic equation. That equation is modified and the strain is taken as 0.002, and this is the ultimate stress, and the yield stress is 0.5 times the ultimate stress, and this 0.002 and sigma c will be 0.5 times sigma cu. Next we have ultimate stress as M30. Sigma c will be M30. So we'll calculate for M30 now, just to cross check whether our calculation is correct or not. We'll match with an paper. So my ultimate stress, I'll enter something like 30. 30 is my ultimate stress, that I'll enter over here. And that's 15. 15 would be 0.5 times of ultimate stress. So that 15 will be my ultimate stress, and the inelastic strain corresponding to ultimate stress will be 0. So let us consider here the ultimate stress 30. Yield stress will be 0.5 times the ultimate stress. First we need to enter the yield stress, and the first point will be my yield stress. So up to yield stress my strain is elastic, and after that I'll have inelastic strain. So let us take any interval up to 30. You can take 15, 20, 15, 20, 25, 30, or you can take multiple values as per your choice. It doesn't matter what you take. It completely depends on you how many data points you'll be taking. Here I have taken 15, 20, 25. You may take other intervals like 15, 17, like that, and you can reach up to 30. But here I'll take up only this just to show you this video. Let's say let's say if you take 17, then you'll simply drag it, but before 30 you should stop, and the next point would be 30, because that 30 is my ultimate point and my yield stress is 15 where the material has yielded. But for the time being, here I'll be just taking these points, and I'll have to find out the strain corresponding to these stresses. and the strength corresponding to stress 30, that is ultimate, is 0.002, which is given from that model Kenton Park. So you can use that model, or you can use any other model that is available on the literatures. There are very models, n numbers of models that are already available in the literature. Here the stresses uh, after the yield point, ultimate point, the stresses after the ultimate point, the different behavior will be there for the stress strain curve. So this should be reducing the stress after 30. Also it should be reducing. If you check the graph, the stress is reducing. So just take any point you want, any interval you want. So whatever strains that will be getting below 0.002 will enter before 0.002, and after the strain that will be getting 0.0 greater than 0.002, that those things will enter after 0.002. This is the yield point, and again ultimate point. Why I'm telling you multiple times, just to make the things clear for you. So the strain corresponding to yield strain, yield stress will be the 0, because inelastic strain at yield point will be 0, but inelastic strain at elastic strain at yield point will be maximum, but inelastic strain at yield point will be 0. So for that point will be 0, but we have to calculate first whatever strain we are calculating. This strain we are calculating, these are not yield strain, these are what is called total strain, and inelastic strain will calculate after that using formula which is given. So just avoid the name. First we need to calculate the total strain, then we'll get the inelastic strain from here. So that sigma c epsilon c dash is my 0.002, and epsilon c we have to calculate. So using this quadratic equation, we have epsilon c square epsilon c, so we'll be getting two roots. So the root which is the strains which are less than 0.002 will be entering before that, and which is greater than 0.0 will be entering after that. So I have calculated this coefficients. Just calculate in the absolute value, and these values we can calculate directly using the stress that we have. So yield stress we have to assume. First we have to assume sigma c, different sigma c, and we'll have to find the stress corresponding to those sigma c. I will also take minus, so it will be easier for us to obtain the results. So simply enter this. So you have got all the coefficient for C. So once you get the coefficient, just type in Google the quadratic equation solver, you'll get this type of equation, this type of calculator. Now you enter the value of A, 2,50,000 minus 2,50,000, which is already given. Then enter the value of B, 1,000, and C you have to enter one by one. This is A, this is B, and this value is C. So C you can enter one by one from Excel. So you enter this value. Now when you solve this, you'll get two roots. Now out of that two roots, as the strains are before, stresses are before the strain 0.002, so we'll take the strain which are less than 0.002 out of the two roots. So take that strain which is less than 0.002 and simply paste over before 0.0, so we'll be pasting it here, and those which are higher than 0.0 will be pasting before 0.002. So over here we need only one root, which will be less than 0.002. So these strains are total strain, these are not elastic strain. I'll change the name. So this just copy this strain. So likewise take the second value, enter over here and solve. So strain which is less than that will be considered here. Same for whatever, how many points you have taken, doesn't matter, just enter those values and take the values to Excel. So done. Now you can cross check here. If you enter the coefficient, you will be getting the strain 0.002. If it is not, if you're not getting that, that means the values are, there are some mistake in your calculation. See, 0.002. So this is a cross check over here. Now for next values you can simply enter, but here we'll take the strains which are greater than 0.002. Why? Because we have crossed the point 0.002. So out of that two root we have to take that. So you calculated all the points and you have got the graph. Once you have calculated all the point and you have got the graph, next is to calculate the inelastic strain. The strain that we have got is total strain. The strain that we have now obtained is total strain. And we need to calculate the inelastic strain. So for inelastic strain we will use the formula. These values you will have to get from any experimental data or use the default values, because these values cannot be calculated. These values you'll have to directly take it, because these are coefficient obtained directly from experiments, so you cannot take those values. Now inelastic strain, to calculate the inelastic strain we'll be using this formula, epsilon c minus sigma c upon E naught. E naught you can calculate directly the stress upon strain. So stress will be my 15, because that is the yield stress, and strain will be corresponding to that strain. So I can directly get the inelastic strain from here. It will be epsilon minus it will be epsilon minus stress upon strain. It will be sigma upon modulus of elasticity. So these values shall be 0. If it is not 0, then your calculation is wrong. So make it constant, because it will be same for all other values. So simply drag it, so you will be getting inelastic. Now this calculation is for M30, I need for M25. So I will now change it to M25, and I need to repeat this calculation again the same way, and using this. So make sure you check all the, you do the calculation based on M25. Once you check with got the M30 value, then you can cross check with the paper which I have attached in the description. You can check with the paper, and for M20 also I'm taking yield stress as 0.5 FCK or 25, so that stress will be like that. And take random values and just proceed with that and solve the way I have shown you. So you'll be getting all the values. I need for M25, that's why I am doing that. So I've got for M25. Now I need to calculate the damage parameters, and the inelastic strain will be same. So damage parameter 1 minus sigma c upon sigma cu, sigma c upon sigma cu is sigma 1 minus sigma c will be the yield stress minus sigma cu I have taken 25. So it will be remain constant for all, so I'm making it constant. So once you calculate, you can get the damage parameter for all. Now there is a thing that if you notice that up to ultimate point the damage parameter will be 0. That means up to ultimate there will be no damage, and after ultimate point the damage will be there. So we have to make sure, see, for M20, 20 is the ultimate point, so up to ultimate point the damage is 0. So here also we will have to do the same thing. We have to make up to this damage parameter is 0, and after that inelastic strain we have to simply copy it. Now for tensile behavior, the stress, the graph directly goes, it reaches at yield point, and again it not yield point, ultimate point, and it fails. So for that we just have to calculate based on that. Now ultimate point, the yield stress for tensile behavior of concrete is 0.5 0.7 under root FCK. So yield stress we can directly get from there, and strain we can directly calculate. We know that modulus of elasticity equal to stress upon strain, so we need strain, then stress upon modulus of elasticity, we can directly get the strain. And other values we can refer this graph. I'll also attach the link of the paper. So next we'll take 2/3 and the ultimate tensile strength, then 3/8, then 1/6. So those stresses will be taken over here. So 2/3 of that yield stress, or whatever say ultimate stress for tensile strength of the concrete, 2/3 of that yield stress. Likewise do it for others, and when you do it, then for strain also it is given epsilon cr, 3 epsilon cr, 5.875 epsilon cr corresponding to the stress. So once you get it, use the same formula to obtain the cracking strain. Then cracking strain will be similar. The strain minus total strain minus same. You have to use the Young's modulus, that is yield stress upon Young's modulus. Then you'll be getting this. Only yield stress will be changing, and the Young's modulus will remain same, and strain will also change, total strain. So we got it. Damage parameter same for yield point up to 8.0. Then you can obtain the other thing. So thank you for tuning into my channel, and if you are new to this channel, please don't forget to subscribe, and if you like this video, please subscribe.